So, while our next speaker gets set up, I'd just like to note that this is one of our student AV chairs. So all of the successes of this, conferences in terms of, AV working is partially thanks to Jan Paul here. So I think we'll probably just give him a round of applause. His hard efforts.
Thank you. I'm up here and it's not an issue, so that must be.
I've jinxed it, haven't I?
Yeah, this is gonna break now. Okay. Disconnect this. Okay.
Okay.
You can change it. Oh, I see. There were issues.
Shouldn't have said anything. I apologize.
Okay, there we go. All right. Okay, so I'll get started. All right, hi everyone. My name is Jan Paul. I'm an undergrad at Cornell, and I'm going to be showing some work I did with my advisor Alwyn at NASA Langley last summer. So this is about software-defined delay-tolerant networks, and to get there, we first have to discuss what a delay-tolerant network is. So delay-tolerant networks are pretty useful for any high-latency disruptive environment, so whether it be trying to communicate via satellites through long distances, like interplanetary distances, or whenever there's any natural disasters, these are going to be pretty useful. So the point of the delay-tolerant network is that we have intermediate nodes that can buffer data for hours or days, hence the delayed aspect of them. And a key thing here, aka the key protocol we want to verify is a bundle protocol. So this resides above the transport layer, and this is what ensures the actual delivery. So now we can look at what are the actual bundle protocols we're going to be working with. So here I'm working with bundle protocol v6 and v7. These are just two bundle protocols that the information I'm working with just deals with. I did not choose them. This is what I was given. There's some slight differences between them, mostly that the bundle protocol v7 has updated block structures and can handle fragmentation differently than the bundle protocol v6, which means that whenever we want to send information from one bundle protocol version to another, as these bundle protocols are going to have different versions when they go from one to the other, we want to make sure that none of the information is lost when having to update the information within these systems. So the main thing we want to make sure here is that the information within these bundle protocols is not incorrect and nothing gets corrupted throughout. So here we have what the information looks like. So now we get into the software-defined delay-tolerant networks. So the software-defined part is just going to be this information. So we have a lower layer Ethernet or an IP header for each packet we want to send through the bundles. And then we actually have the bundle. So the bundle is just the block containing the specific field metadata that includes the version and whatever other data we need. And then we have, we might conditionally rewrite or parse these fields for each bundle protocol. So then, by layering the software-defined network on top, now we have a centralized hierarchical controller. And in this controller, this is when we can get into the programming languages part. So this controller installs something called the match action rules, typically programmed in a network language like P4. And we just want to ensure that these rules don't introduce any packet corruption. So this is a quick simplified sketch. So what we have is that we have each cluster being a controller, and then each node runs a data plane, and this is where the P4 code lives. So the links between clusters might be intermittent, hence the delay, and this is why we have the red dashed line showing the delay tolerant part. And we just want to make sure that within the existing clusters and then going from one cluster to the other, that this match action pipeline, which is what goes from one cluster to the other, matches the information in a secure way. We want to make sure that this is safe. So there's some basics here. So we can step back from the actual programming languages of P4, and we can just look at general calculus, an abstraction just called the network calculus. So this is pretty well founded. There's a lot of papers that discuss how to formalize network calculus. So this part is pretty straightforward here. So the main two things we want to show here are the bounding queue buildup and latency guarantees. So we have a couple of things here. So we have a cumulative function such that for A of t, this measures the data arrival by time. Then we have a minimal service guarantee via the service curve as well. And then I'll explain what this min plus convolution is doing there in the middle between the A and the beta. And then we also have the min plus convolution. It's just a pipeline composition. So I guess, yeah, okay. All right, so here we get to it. So, so diodes are going to be the core of this network calculus. So we have the O+, which is typically just min. So this is going to reason about aggregate functions like min of A and B to simulate or model bounding. Then we actually have the min plus convolution from the minimal service curve guarantees. So in here, we can just say, so for a server S1 that has a service curve of beta 1 and a server S2 that has a service curve of beta 2, then their cascade has a service curve of B1 O times B2. This is the min plus convolution. And now you can see how it makes sense here with the arrival time and the additional now beta of t insurance. We also have a couple of other things here. So we have the absorbing element, and we also have the identity element. So identity just gives us, so if a stage is no delay, no loss, it doesn't reduce service. And the absorbing element is just to give us information for when the entire pipeline can effectively deliver 0 data. So this gives us a framework for reasoning about the network abstraction. So these are, excuse the badly formatted LaTeX there, but this is how it was simulated in Coq here. So we just have a cumulative function at CF1. Here, this is the actual function A of t describing how much data arrived by a time t. Then we also have the non-decrement. So this is just a sketch here for the proof that A of t never decreases as the t time increases. And we also have some proof that A of 0 for a time 0 equals 0. So these are just some basic proofs to be able to give some abstract guarantees about an arbitrary network that would be that would use this calculus. So going forward here, I'm going to skip through the actual description of that, and I'm just going to go to the programming language part. So back to P4. So I was given a match action pipeline, which is an algorithm implemented in P4 that manages the network flow. And what we want to do here now is I have a network calculus that has certain guarantees proved in Coq, but the actual P4 code still doesn't have any guarantees whatsoever, and it doesn't really interact with the calculus I've abstractly defined. So we obviously know that you could mechanize some P4 code, I guess, if you have some way of mechanizing it, but that's pretty hard because P4 is large and complex. So instead, what we want to do here is that we want to define a subset of P4 that is expressive enough to only deal with the match action pipeline, which I'll describe what that includes in a second here. But that we can still target with our Coq representation. So this is a bit of the grammar for how this P4 subset is going to be defined. So we just have a program P that has multiple declarations followed by a control block. And then what a declaration can have is either a header, and the header has fields with their types. We have an action definition specifying the type parameters and a body statement. And then we also have a table definition listing keys, which are at either header fields or expressions and possible actions. The actions here being if we want to send a packet or we want to drop it from the information or if we just want to hold it. Then we have the control block. So this simply apply for a statement S. Then we have our generic statements for control flow and expressions for simple arithmetic. And so here are two, again, simplified semantics for this subset. So what we have here, we can have a small step operational semantics in which we have a tuple, so we have a sigma and a packet. So then in T action, this shows how the action is going to be executed. So we just look up the action body for body of A, this is typically just going to be a list of assignments. So we just enumerate those assignments, and these are just going to be expressions, and we just evaluate these expressions and then update the packets accordingly. Pretty straightforward there. And then for tapply, this is going to cover the table application. So if the table match picks an action A, we then run that action small step execution. And of course, there's more so for control flow and sequential composition and assignment here for the packet header fields. So there's something important here we have to take into consideration, which is why this subset is actually sound for, quote, normal P4. Again, I'm given P4 code, and then the idea here is that I want to be able to try and make it so whatever code they give me still works within these semantics, but I don't want to overcomplicate my semantics still. So I've just focused here on these core constructs from the match action pipeline. So it's just headers for the field definitions, tables for match, actions for field updates, and the basic control flow. I'm pretty much ignoring any more advanced P4 feature, as well as omitting specialized hardware-bound P4 features as well. So now we can see how exactly I want to use this small P4 subset. So the idea here now is that I have a network calculus, and this network calculus has proofs, and now I have a language that can actually interact with Coq in some way, because it is separate from P4. So what I now need is some sort of IR in which I can compile this subset of P4 into some Coq representation that can then go through the Coq proofs I did earlier, and then we can actually see if whatever match action pipeline, so this very specific type of algorithm, whether this is correct or not. So here we just replicate the P4 subset structures again, and we define. So now this is how it looks like in Coq for what I call NetQIR. And now we can get into the actual semantics of NetQIR. So now we can go back and we can start connecting with the network calculus. So here we have flowspec, which is a function that for each NetQIR statement, it returns a service curve describing the minimal guaranteed service. The NetQIR language ensures statements are safe from this rewriting perspective. And while the flowspec ensures, we can also talk about the timing and throughput guarantees through this definition here. So as an example, we can say that if we can say that for the invoking of an action, that invocation corresponds to 1 millisecond of processing, then we can model that processing delay as a simple beta. The beta of t delayed is going to equal just the max of either 0 or the total amount of time minus the delay 1 millisecond. So this is implemented then in the composition rule. So we have now for the composition of S1 and S2 for flowspec, we have the simulation of the cascade composition in the network calculus. So we say if stage 1 here, so you can see at the top of the slide, so if stage 1 has beta 1 and stage 2 has beta 2, the overall pipeline has then B1 O times B2, connecting the network calculus to this language now. So now that we've unified this flow bounding perspective from the network calculus in this language, the idea here is to show that no matter the arrival function A, we get a departure D satisfying the typical network calculus inequalities for whatever NetQIR program we define, for whatever function we write in it. So this is the end-to-end theorem in NetQIR. So we have this hypothesis that just means that if P is well-typed in NetQIR's type system, then this prevents ill-formed statements. So this can be, for example, writing a bit 16 into a bit 8 field, which is important. If we go back to the bundle protocol versions, they have different sizes for these fields. So it really matters how we want to, it really matters to make sure that we don't end up overflowing the wrong version because of this. So the conclusion has 2 parts here. So we have the first part, so for that, the formula on the second bullet point there, which states that the classical service curve-based performance is guaranteed from the network calculus, and that no unintended packet duplication or corruption is captured in the semantic correctness of the language, which just means that actions and tables don't create new packets from nowhere or miswrite them incorrectly. So yeah, basically in practice, flow spec of P is defined by associating a curve to each statement. So then we can go here to the overall compilation pipeline diagram, in which we parse the P4 subset, we check the types, then we translate this to each statement to NetQIR, aligning the semantics. Then the NetQIR code is fed into Coq, and then we apply the proven results. So in this case, it would be just the packet correctness and the network calculus flow bounds. And then if something fails, like a type mismatch, we feed back an error message. So now the important part here is we need some sort of type preserving compilation process to make sure that whatever subset of P4 we have to find when going into NetQIR, it actually preserves. So then what we are mechanizing is essentially the same as what we did not mechanize, which is the P4 code. So here we just have the compilation function, translates each P4 construct to its NetQIR counterpart. And here we have a couple of things. So we have an action. So for this action, the compiler extracts each assignment from the P4 body and then converts it into one of NetQIR's sassigned statements. So for example, for parameter types, so for like bit 32, this becomes T-bit of 32 in NetQIR. And all these statements are wrapped into a NetQIR action block with the same name. In this case, it would be the name A, since that's what we have here for an action A. We also have then the table. So for a P4 table listing key fields and possible actions, this is mapped to the S table apply of T. And then the logic is reasoned about in NetQIR with our T table, T apply rule I showed earlier. And we also reason about the typing environment in this similar way. Then we have, so then we have the well-typeness preservation here. So so if the P4 program passes the P4 type checker, so this means that there's no mismatch between bit widths, action parameters or whatever between the two bundle protocols, then the resulting NetQIR program is well typed. And this is essentially to reuse the NetQIR theorems for packet correctness and flow bounding here. So that gives us, that gives us the basics for how NetQIR works. Then we also have here the some proof mechanisms, but for the sake of time, I'll skip that now and I'll just go to the example here. So this is an example from the original P4 code. I just cut it and then modified it a bit for it to make sense in my subset of P4. So Here, we just set the egress port and rewrite the MAC address and then decrement the time to live, the TTL. So then, yeah, in the SDDTN context, this would be the equivalent of rewriting the bundle protocol version block or setting a priority. And then now we can look here, the compile NetQIR plus flow spec version of it after it goes through the pipeline. So you can see the compiler yields the NetQIR action with the 4 S-assigned statements. We attach the identity service curve or the slight shift to each assign, and the inductive Coq proofs then shows that the final packet fields match the intended rewriting for the original minimal service guarantees. So finally, to put it all together then, we have then that for a NetQIR program that is well typed, and the program must use these correct assignments and references. The flow spec of P assigns the service curve to each statement. So in this case, we have IPv4 forward. So for this function, each field update is effectively has effectively a 0 delay in the abstract model, in the network calculus model. So the total service curve might remain as the identity for the actual implementation of this. So there is no delay here. So from the network calculus, we know that any arrival function A into that pipeline is lower bounded by A star beta forward for whatever given time, and the at the output D of t. And then for the Coq proof here, so for the base case, we had that a single S-assign modifies exactly one packet field, preserving the rest. So correctness of rewriting is immediate here. We have that flow spec as identity, and then for the inductive step, we just run this on the sequence of statements composed by O times. And yeah, so then to conclude then, we have a combined minimal P4 subset, which just targets this match action pipeline with this specific IR, NetQIR, to ease the verification and to indirectly mechanize this algorithm for converting from a bundle protocol v6 to bundle protocol v7 stores and forwards. So you could have the P4 code separately, just feed it through a pipeline, and then you would know if this specific, the specific functions you called for these bundle protocols is correct or not. So for possible directions here, there's more to do in the terms of the bundle protocol features. As you saw, I'm only giving minimal service curves here, and there's a lot more like handling full bundle protocol fragmentation or custody signaling. There's also obviously expanding for the entirety, or not entirety, but a more broad set for P4 or other languages as well. And obviously, there's also testing it on actual NASA testbeds, which hasn't been done. It's only been compiled, but it hasn't actually been tested with deployed code. And then the renaming, because I named this NetQIR, the Q from Coq, but as Coq is now Rock, then possibly rename it to RockNet or Rocket. And that is it. All right, thank you.
So we're a little bit behind, but we have time for questions if there are any questions. I have one quick one. So in your theorem, maybe a couple slides back, this D, where does anyone, yeah, whatever the theorem, this one, where does D come from here, right? So A is universally quantified. What is the connection between the departure D and the arrival function? Where does D come from?
So D is just it's not the arrival function, it's just the destination time. So it's just going to be, that's defined over here. Let me find it. Yeah, here. So you're always going to have that the destination is always going to be greater or equal to the arrival time here for showing continuous flow in the network.
So does D depend on the input program, or D? So D is just a constant? I guess I'm
Yeah, D is dependent on the input program.
Okay. So
yeah, this was
it's
in,
implicitly hidden maybe
Yeah.
in the compilation. Okay, so that makes a lot more sense. Yeah.
Yeah, this was in one of the examples. Sorry, it seems I don't have it on the screen, but this is in the example for when you have the corresponding delay for like 1 millisecond, then that would be within the arrival time there. That'd be the delay. So you'd have whatever t minus the total delay.
Yeah. Okay, that makes sense.
Yeah.
So, any other questions? Well, if not, let's thank Jan Paul again. And
All right. Thanks.